So then, going back to the lesson on the linear algebra kind of mathematical preliminaries, we talked about how tensors or matrices are transformed through a coordinate transformation or rotation. And so if we're given S, so in this case, S is the principal stresses, S1, S2, S3, and it's diagonal, okay? Then we find RG via that equation, and then we just plug in RG transpose S RG, and that will give us that will transform the stress back into the geographic frame. Oops. So let's work an example. Anybody got a calculator? So your angles are 0, 0, 90, right? So I'm going to go back a couple slides, but remember that, 0, 0, 90. I'm going to go back to here so you can plug them in, right? So alpha 0, alpha is 0, beta is 0, gamma is 90 degrees, right? So what's the cosine of 0? 1 times the cosine of 0, 1. 1 times 1 is 1, right? This one has a sine of 0, which is 0, so that whole thing is going to be 0. This has a sine of 0, so that's 0. Maybe you don't need your calculator. Right? This has a sine of 0. This has a sine of 0, so that's 0 minus 0. This has a sine of 0. Now we have cosine of 0, which is 1, but then we have the cosine of 90, which is what? 0. Okay, now we have the cosine of 0, which is 1, times the sine of 90, which is 1, right? So this guy is 1. And we have another sine of 0, so that's 0. We have a sine of 0, so that's 0. We have a sine of 0, so that's 0. We have the cosine of 0, which is 1, and the sine of 90, which is 1. We have a negative sign out here, so that entry is going to be minus 1. Okay. And then we have the cosine of 90, which is 0, so that's going to be 0. Right? So what we end up with for this problem is 1, 0, 0, 0, 0, 1, 0, minus 1, 0. Right? So back to the problem here. Right? Okay, so now we also need R transpose. It may be that in the linear algebra lesson I had written, well, the transformation would be like SG R inverse SR, okay? And I told you that all, we talked about that all unitary matrices, their inverse is their transpose, and that's true for eigenvectors, right? If the eigenvectors are normal vectors, then you have a unitary matrix and its inverse is its transpose. Well, it's the same thing for rotation matrices. All rotation matrices are unitary, okay? And so their inverse is their transpose, which is nice because it's much easier to transpose a matrix than to find its inverse. But anyway, so we'll need the R transpose, and you know, that's just, we're just going to take the columns of RG and make them the rows of R transpose, right? So that's just 1, 0, 0, 0, 0, minus 1, 0, 1, 0. Right? And so then we need to do this multiplication. I like to do them one at a time. So we have S times R. So we're going to do this part first. S times R. All right, so S is just as it's written there. R is so we need to do this multiplication, right? So everybody remember how to multiply vectors, or matrices rather? So the first entry here is going to be the first column of this guy dotted with the first row of that guy, right? So that's basically that the dot product of this vector with that vector. So that's just 30 times 1, and all the other entries are 0, right? So it's going to be 30 there. Then this entry is the dot product of the second column of R with the first row of S. So that's clearly 0, right? The third entry is going to be the dot product of the third column of R with the first row of S. And that's again going to be 0. All right. This entry, right, what is this entry? Okay. In words, the operation, though. Just so you get it clear. It's the first column of this of R with the second row, right? And so that's going to be 0. And then this term here will be the second column of R with the second row. That's also going to be 0. What about the last one? The last column with the second row is going to be 25. Okay. And then I'll just write down the last row. Right, so that's SR. So then we need to multiply that on the right side by R transpose, okay? So R transpose SR is, R transpose is this guy. And if you work through it, then you get okay. So that is SG. All right. So you notice that SG and S are different. Now, in this case, they both happen to still be diagonal, but that may not always be the case, okay? I think there's an example. I have another example that won't be the case. All right. So one of the reasons I wanted to go ahead and type that in Mathematica was so that it would be there. Because you know, this is a perfect candidate to you know, this would take a long time to type into your calculator. How many of you have programmable calculators, like a TI-89 or an HP40, like one of those, a calculator you can program? I imagine you all do. You just don't know you do. You probably never programmed it, right? But you could. I mean, I think just had a thought. We may take our tests on the computer right, so that you have Matlab open. Because, you know, I don't want you on a test to be stressed. This is not hard, right? It's just literally plugging and chugging. But this is like a perfect candidate that if I can write a function that just takes alpha, beta, and gamma and it computes this for me, and it'll always be right. And I was going to tell you that you should program your calculator to do that, but if you don't all have that calculator, just to make things fair, we may take the test in the computer app. But anyway, so what I'm going to do, since I have it here, I'm just going to write a function real quick. And you know, I'm going to use Mathematica just because this is already here. I don't want to open up Matlab and retype all that other stuff. I already have the correct formula. So I'm just going to use Mathematica, but you could easily do this in Matlab, right? So I'm going to create a function that's going to take as arguments alpha, beta, and gamma. And then that function is going to return the rotation matrix. So the module is sort of Mathematica's word for function. So pretty simple function. We had 0, 0, and 90 degree. The default is to use radian in Mathematica. That's right? That's what we got. Right? So, I mean, this is why I love computers. I, in the notes, gave you a test for any code you could write. It's a really simple code, right? But it's a little function that computes the rotation matrix. And I gave you the correct answer. So if you can reproduce this answer, you should never get this wrong. Ever. Right? And I have other examples, but so we could actually just go ahead and take it a step further. We could create another function. So I have another function that I'll call SG, and it'll take in the stress tensor, the diagonal. It'll take in the stress, okay, and alpha. I'll just copy this. Alpha, beta, gamma. So there's another function. It'll have a local variable RG. And so inside this function, I'm going to call the other one. And so I'm going to say RG is equal to that. And then I'm going to return RG, the transpose of RG dotted with S dotted with RG. And so then let's call that function so the stress was 30, 0, 0, 0, 0, I'm sorry, 0, 25, 0, 0, 0, 20, alpha, 0, 0, 90 degree. And I get back 30, 20, 25. 30, 20, 25. So here are the correct answers to test a potential future code you're going to write. One that I just wrote. Okay? So now that we have a code, let's test it for some other problems. Right? So my stress is 30, 25, 20, and I have 0, minus 90, 0. $30, 25, 20. That's the same, right? 30, 25, 20. The angles are minus 90, 0. The answers are 20, 25, 30. 20, 25, 30. The code works for that problem too. So now I have 30, 25, 20, and I have 90, 0, 0. So same stress, and I have 90, 0, 0. And the answer is 25, 30, 20. 25, 30, 20. Okay. So here's a little bit different one. I have 60, 40, 35. 60, 40, 35, and 135, 0, 90. And I suspect my answers are not in rational numbers. All right, 47 and a half minus 12 and a half looks good. Minus 12 and a half, 47 and a half, 40. Correct. Right. And so, and this is one case where you see that in all the other cases, while the transformed stress, the stress in the geographic coordinates was also diagonal, in this case it's not, right? We start with a diagonal, and we end up with something that's a full stress tensor. Okay? They'll always be a diagonal as long as these are non-zero. If one of these were 0 for some reason, which would be odd in the Earth, but if it were, then you'd also have a 0 there. But should be. I guess potentially you could have a 0 there, but yeah, it should be. You have to look at the figure, right? It's positive as it's drawn in the figure. And that's why the sort of sign of the angles is so important. It's positive as it's drawn on the figure. So if I give you one of these problems, I'll always give you that figure, and the angles on that figure will never change. They are in the notes as they are in the book, and so you just have to look at that. And I know, last year when I taught this class, a lot of the students had trouble trying to figure out which rotation was which. If that's the case, go back and look at the, I worked through the example of the 3 isolated rotations, right? With that, you can clearly see which, if you look at them in isolation, you can clearly see which angle is which, okay? So, honestly, there's really no, I mean, if you just sort of follow what I did here, write yourself a little program, there's no reason to ever get one of these problems wrong. Because I gave you the tests, right? So whenever you write code, you should always verify your code. When verify means you test it against some known solution. I gave you in the notes known solutions, right? So you can write a little piece of code, test your code against the known solutions, and then any other problem I give you, it'll work. Right? It's already been tested. So really, the only challenge on the homework is I'm going to give you a homework, and you're going to have to do some of these. And the only challenge is going to be figure out which angle is which. Right? Get the angles correct. And if you get the angles correct, it's a piece of cake. There's no excuse to get it wrong. Yeah, and you don't have to. The only reason I'm using Mathematica is because I started off because I want to do the symbolic computations so that you could see that this matrix looked exactly like it did in the notes. And the only reason I'm using it is so that I can just copy and paste it and I don't have to type all that in. Otherwise, I would have done this in Matlab. And if you want to use Matlab, it's fine. But yeah, the syntax here is that this is the name of the function is RG, and these are arguments, okay? And the underscores just tell, whatever is in the function body, which is this part of the code, that those things with underscores, you just pass them through, right? They just, whatever is there goes there. Those are the arguments to the function. And then this is what's returned. It's pretty close. Yeah, and pretty close. I mean, in Matlab, you over here you say what arguments are going to be returned, and then you say function something whatever. Yeah. And of course, in Matlab, and one reason I sort of don't like it is all your functions have to be in their own files, right? You have to have a function file. And this can be sort of annoying because good programming practices encourage really small functions. Right? If you have really small functions, they're easy to test, right? You notice when I defined this second function, so this is a small function. It just computes the rotation matrix. This is another function that calls my first small function. Right? And the reason, good programming practice would be because I can test this in isolation. I can compute the rotation matrix first and know that it's correct. Right? And then once I test it and know it's correct, I can move on in my coding and always assume that if there's a future mistake in my code, it's not due to that. I've already tested that in isolation. Okay? And then as I continue on, I write more code. I mean, this is a pretty simple code, but if this code were to produce a mistake, it wouldn't be because of that line. There's only one, and so there's only one other line in the code. So if this code were to produce a mistake, it would have to be due to this. So it makes debugging easier. Right? So good coding practices encourage you to write small functions, which means in Matlab you had, if you have small functions, you have 100 files on your file system to write one program because you have to have all these small. Whereas here in Mathematica and in Python and most other computing languages, you can C, Fortran, whatever, you can have your functions in the same file as the rest of the code.